Welcome to a lesson with Dr. Powell. Let's take a look at an example of finding the invariant subspaces associated with a action of a matrix. So here's our matrix that we're going to do. First step is to do some column operations until it's pretty clear that row operations would finish us off to get us a diagonal matrix here when we think about x minus this matrix. So xi minus a, that's what this is right here, xi minus a. So at least the entries, that's what that represents right here. So we do a couple, in fact, we just do three kind of airdropping things. To get to a point to get to right here. Now it's clear that row operations would finish us off because with just airdropping even because we can multiply this by because these two guys are basically just there's are multiples of each other. So you could multiply this guy by -1/2 and add it down, clear that one out. And this guy right here can easily clear out these. So that looks great because we never have to divide by a polynomial where we have x having a power bigger than 0. So that's nice. Okay, so taking a look at this, in this case, this is where it takes us to, we can kind of review what we're doing. Like, how did we get this? I mean, I just found something like this, put something in the corner. In fact, I was doing it kind of in an odd diagonal sense here, but you could rearrange what we're doing. So it could be a 4 diagonal, but nonetheless, we just need to minimally do what we can with columns, and then rows can finish us off here. So I just picked something that was already in the corner. The 4 was in the corner, and I could do an airdrop over this way to make this guy a 0. Of course, that changed that one, and that changed that one too. So multiplying by 1/2 and then adding over. Now over here to make this guy a 0 here required me to multiply this whole guy by -4 x minus 1. So that's a 0, but then that changes these guys. Okay, so we got something there, right? So we did 2 things to clear off with zeros. And then next, next in the process, looks like I wanted to make, so I have a 0, 0 something. So that maybe I can make a 0 there. In fact, look nice because these were multiples of each other. If I just multiply this by 1/2 and then added it over, voila, it's a 0. And then over here, I get something if I add them together. So expand, add, factor out -4, end up getting this. Okay. And that looks good. All right. So row operations could finish us off this point as we explained. Now we have, we look at the columns that we have currently right here and we factor out whatever's common. So we did that, this, this, this. All right, so it looks like we'll be having 2 invariant subspaces. This guy is just going to go to 0 because this is, I mean, modding out by 1 just gives you 0. Here, this is going to give you something degree 1. This is going to give you something degree 2. So we have a degree 1 subspace and a degree 2 subspace that are invariant with respect to the action of that matrix. Okay, so let's look at what we have so far. So degree 1 are right remainders. That's when we have a when we're modding out by something degree 2, we'll get degree 1, but that degree 1 polynomials have 2 things in them, the x term and the constant term. So you have 2 different real number coefficients there. It's going to give you something isomorphic to R2. In fact, we have a basis for here 2 linearly independent vectors. How do we get them? Well, we just simply look at this guy's coming from this column, the 0, 0, 1, right? So we take 0, 0, 1, and then we have x times 0, 0, 1. So the action on it. So we think of the matrix. This picks out the last column. So really, that guy and that guy, that's the invariant subspace that we're looking for, the first one. The next one, degree 0 remainders, either meaning constants. That's because we're modding out by a degree 1 polynomial, modding out by x minus 1. So we're going to be, basically, it's just that vector then. That's kind of nice. We don't have to do any x to it. It's just that. Action of A is a scalar is closed on these subspaces, does not take us out of them at all. Okay, and then the last thing let's look at is the minimum polynomial overall is what? The least common multiple of x minus 1 and x squared minus 3x plus 2, which is the same thing as x minus 2, x minus 1. So since that's a factor of that, hey, that's the minimal polynomial right there. Okay, x squared minus 3x plus 2 wins. We got the minimal polynomial, meaning that we put the matrix in here for x, we actually get the zero matrix. It would exactly be equal to it. Thanks for watching.